All right, hello. So this is first lecture for chapter three. As I said yesterday, we're going to start splitting them up into shorter videos where it's easier for you to manage um, and kind of take out when you have time instead of having a big hour and a half long video that you have to kind of come back and get to when you can. I'm going to try to do shorter videos. Uh, but I'll post more of them. So I'll probably post another one tomorrow where we finish chapter three, whatever we didn't get to today. I'm doing it a little shorter today, also because you have a lab that I'm going to post this afternoon or this evening. Um, I don't know, probably around 5 or 6. Okay, so be on the lookout for that. Um, anyway, so today we're doing chapter three, and this is matter and energy, and we'll probably stop before we get deep into the energy portion. But I did post, or I will be posting. I haven't yet. Slides for chapter three, and then I've been getting emails. So most everybody's gotten their stuff in, but some people still are having problems, especially with the lab manuals. So I've been communicating back. I'm going to work with you best I can. Everything is due this weekend, Sunday by midnight. So if you haven't emailed me and let me know your situation, please do so. Um, I may have to take off some points. I haven't decided yet. We'll see uh, how it shakes out, but I expect that everybody should be able to finish the Master in Chemistry assignments on time. Even if you don't have your book, I've provided enough other materials that would allow you to go in there. If you don't have access to Master in Chemistry yet, say you're waiting on an access code, you can do the temporary access. It's like a 14-day trial or something like that. Um, that will get you into the program. You can sign in, do the assignments, and then enter your access code whenever it comes in. I would rather you do that than have to catch up whenever your access code comes in, and then also depend on me not giving you a late penalty. There's a lot more variation in that scenario, right, that you can't account for. So um, get the trial version, go ahead and knock out the Master in Chemistry, and then put the access code in when it gets here, okay? That way you don't fall behind in the lecture course. Now, as far as for the lab manual, I'll address that when I send out the videos to the labs, but there's not really much you can do about that. If you don't have the lab manual, it's going to be hard for you to answer the questions. Uh, yeah, like I said, I'll post that in the lab. But let's get into chapter three. So on the PowerPoints, you'll see this list of vocabulary words. Those are in alphabetical order. Um, and if I don't mention it, it's probably not that important. But I imagine I'll talk about a little bit of everything on this list. So let's look at the text real quick. I want to start here for those of you who don't have access to it yet. Um, kind of go through here. I don't know if you can blow this up and maybe you can read everything yourself. But we're talking about matter. Okay, so everybody kind of has a sense of what matter is, right? So matter is anything that has weight. We call mass, that has mass and occupies space. So it takes up some kind of space in the world, and it also has some type of mass or weight in the world. Now this can be a little abstract, like air. Air, believe it or not, has weight. If I take a bottle, a jar or whatever, and I capture some air and I weigh it, it'd be heavier than if I managed to get all of that air out of the jar somehow, vacuum seal it or whatever. Without air in it, it would be lighter. Okay, so air does have weight and it does occupy space, but you just can't see it. Okay, um, but we know it occupies space because when we breathe in, it fills our lungs, right? So, like I said, it's kind of abstract. Some things that are not matter but exist in the world would be like wind, sunlight, uh, radiation. Yeah, I guess radiation doesn't have weight, and technically it doesn't. occupies space. So like radio waves, right? Radio waves move through the atmosphere. They don't really uh, they don't take up the space of the air, right? Air just kind of passes through them. So radio waves would be not matter, all right? Matter, something that has mass, occupies space. Different types of matter. There are pure substances or excuse me, there are two types of pure substances. So a pure substance is just something that's uniform throughout. It's the same little atoms and elements or whatever all the way throughout the compound. Let me go to the slides and see if there's something better on there to kind of illustrate. What's wrong with the thing? Okay. So chapter 3 preview. So here are the classifications of matter. There are pure substances and there are mixtures. Okay. We classify pure substances as elements and compounds. When we say a pure substance, that means that I can take any one little piece of this material and it'll have the same chemical composition and characteristics as any other piece of that material. Say a glass of water, right? If I go in and grab one water out of the bottom corner and then I grab one water out of the top corner, are the two things identical? Yes, they're the same type of water. This is a pure substance, right? As far as I know. Like I said, you can't have like little specks of dirt and stuff in there you can't really see, but that would make it not pure. Okay, like Flint drinking water or something. A mixture contains two or more different substances. So, like we were saying, Flint drinking water contains lead uh, and also water, probably a lot of other stuff. So, in that sense, it's a mixture. I like to think about sand and dirt and stuff. When I pick up dirt, I don't just see Georgia clay, I see little rocks and pebbles and all different types of stuff. That is a mixture. Okay, a pure substance would be if I just had red Georgia clay and I could pull out any individual piece and it would all be the same clay. All right, so that's like a pure substance. All right. Now we classify, you'll see here on this little diagram, we classify pure substances as elements and compounds. Okay, so an element is the simplest substance that anything can be broken down. All right. Let me pull up a periodic table. So everybody should be familiar. We talked about this our whole lives, right? So these are the elements. This is called a periodic table. Your elements are listed here. If you want to know whether or not a substance that you're looking at is an element or something else, you could come here. If it says I have helium and I see helium here on my list of elements, it is an element, okay? A compound consists of more than one element. So it'll have nitrogen and oxygen, like nitrous oxide. That will be a compound. Okay. Now the difference is the important thing to keep in mind is that a compound is the same throughout, which makes it different than a mixture, which has different portions throughout the substance. Okay, throughout the the substance, whatever you're looking at. So compound is composed of two or more elements that are combined in the same proportion. Okay, so here's a periodic table. And like I said, if you're curious as to whether you're looking at a element or a compound, you can come here. If it's not here, but it's the same all the way throughout, then it's more likely a compound. Okay, so you can do that as a tester. We'll look at some examples here in just a second, and I'll show you what I mean. Okay, so here are some examples of compounds. You'll notice that all of these have more than one element. This one has hydrogen and oxygen. This one has sodium and chloride, carbon, hydrogen, oxygen, but they have them in different amounts, right? So hydrogen peroxide is hydrogen peroxide all the way throughout. I have a bottle of hydrogen peroxide. I can pull out any individual molecules, and there'll be a bunch of these H2O2s stacked together or like floating around each other. Salt is the same way. When you put salt in the water, it breaks down into all these little NaCl's. Um, but when it's together, it's just NaCl. There's nothing else there, so that makes it a compound, right? All of it is just NaCl. Um, Sugar and water obviously are the same way. So when we're talking about mixtures, remember mixture is what we talked about like with the sand and the dirt, where I have different compounds, okay? An element makes up compounds, and multiple compounds and elements make up mixtures. And that's a good way to think about it. So there's two different type of mixtures: heterogeneous and homogeneous. And homogeneous means that everything is essentially looks the same. Okay. Uh, for example, let me think. Salt water. Okay. We just said that salt, NaCl. Let me go back to this page here. Is a compound. Correct. Water, H2O, is a compound. Now, if I combine these two and I make salt water, you can't see the salt if it's hot water, or if you don't have too much salt, the salt dissolves in the water. You can't see it anymore. So if I were just looking at a glass of salt water, I may think that that is just water, but I know that it's not. It has salt in there as well, so that makes it a mixture. Okay, and since I can't tell it's a mixture, it's a homogeneous mixture. It's all the same. Okay, now the dirt, on the other hand, I can look at it and see the differences within it. That's a heterogeneous mixture. Okay, so hetero meaning different. It has different mixtures within the mixture. Homogeneous means it has the same. It's all the same mixture. Okay, throughout the whole substance, it would be the same. I think we got some examples of that. Let's see, homogeneous mixtures. So they use the gases that divers would use when so oxygen, nitrogen, oxygen, helium, nitrogen. These are all combined in a tank, and you can't tell that they're combined at different ratios. You can't tell even that there's different gases in there. If you were to look inside the tank, you would just see essentially air. But there are different elements in there, and multiple elements and multiple compounds means it's a mixture. Okay? So composition is uniform throughout, and I'll have a lot of examples on Master in Chemistry, and then your text also has some examples. Um, so yeah, it's you'll get it. It's pretty simple. Once you start just going through and like work and practice, you'll see the different examples. They'll give you, I think, seawater. So if you notice, there's a difference between salt water and seawater. If I grab a hand of seawater, I'm probably going to have some sand in there. Okay, so that'd be a heterogeneous mixture. But we just talked about salt water. If I just mix salt in, I can't tell the difference, and therefore it's a homogeneous mixture. So be careful. You'll see some kind of like little tricks like that. Another, let's say, heterogeneous, a bowl of cereal, right? I got some solid pieces, I got some liquid pieces. Anything that exists in two different forms, say a solid and a liquid, or an oil and a water. You notice sometimes if you have oil and water, they'll sit on top of each other because one is less dense. Then that would be a mixture. You know it's a mixture. Even if they separated and you mixed them back up and you couldn't see the separation no more, we still know it's a mixture. All right. So yeah, classification of matter is not that bad. Let's do here are some practice. So I said if it's in two different states, right? Solid and liquid, as in the case with the pasta and tomato, then that's obviously a mixture. So it wants us to classify as a pure substance or a mixture, but we'll take it even further. I'll say this is a heterogeneous mixture. All right. Aluminum foil. Okay, so let's think about this one for a second. Aluminum foil If I lay out a sheet of aluminum foil, it looks the same all the way throughout. If I grab this corner of aluminum foil, rip it off, look at it, examine it, it's going to be the same composition of the middle of the aluminum foil. Okay, so that means it is a pure substance. Now I need to determine whether or not it is an element. Now you may not know this, but aluminum as by itself wouldn't be able to make that foil. You have to have other elements in there to combine the aluminum. Therefore, I'm going to say it's a pure substance and it's a compound. Okay? Helium. That one's easy enough. I know helium is the second element on the periodic table, so it is obviously a pure substance. It's an element. Unfiltered air. Okay, so unfiltered air means that it has particles floating in there, probably some dust and some other little things that, I mean, is in everybody's air. So I would say that is a mixture, and I wouldn't be able to see the dust particles more than likely unless I had a device of some type. So I'll say that is a homogeneous mixture. Okay? So that's how I do those problems. I just think about what the material is that I'm talking about, and then how can I break it down, right? If I cut off one portion of it, is it different than another portion of it? And well, you get it. Okay, homogeneous or heterogeneous. A hot fudge sundae had the ice cream is more or less solid, the fudge is more or less a liquid, so that's obviously a heterogeneous mixture. If it has two different states of matter, it's automatically heterogeneous. Okay. Shampoo. If I look at a bottle of shampoo, it all looks the same. So I'm gonna say that's homogeneous. Okay. Sugar water all looks the same as well if it's properly dissolved. So I'm gonna say that's homogeneous. And then a peach pie, same thing. It has little physical, little solid pieces in there with the peach, but then you also have like the sugary, syrupy stuff in there. That's got to be a heterogeneous mixture. Okay. So you see how to do this, right? Okay, so I was talking about the different states of matter. Now, this is also something that we've done growing up. Solid, liquid, gas. And they got this plasma on there that has to do with like lasers and stuff, but we're not worried about that. Gas, solid, liquid. Okay, SLG. You'll see that every now and again. Let me pull up my iPad for y'all, so because I want to show y'all something about the solid, liquid, gas stuff. So we know that solids are they hold their shape, and I've got the different properties here of the different ones, but I wanted to show y'all this first. Let me make sure my iPad's up and running. Bop, bop, bop. iPad transition. Okay, so for a solid, and we'll talk about what they are here in just a second. Liquid, and I didn't get my pen, that's why this writing is really bad right now. Solid, liquid, gas. It should be filling in. It'll fill in eventually. Solid, liquid, gas. Okay, come on, fill in. It's trying to. So these are some symbols that you'll see that should tell you that it's a solid, liquid, or gas. Why did it do that? Looks like I might have to come back to this. I checked it before I got started and it was working fine. Oh, that sucks. Alright, never mind. We'll get to it when we start doing chemical equations, but there are some symbols that we use to denote solid, liquid, gas. So anyway, states of matter. Solid has a definite shape, right? And a definite volume means that if I sit it on a table, it won't just spread out and fall all over the table, okay? Something that spreads out and falls all over the table, we call a liquid, because a liquid has an indefinite shape and it fits the shape of the container, right? So there are some similarities and differences between the different states of matter that you can kind of use to decipher which one they are if you're having trouble with. Okay, so remember, solids pretty much hold their shape. They don't just fall apart and uh, fill the shape of the container they're in. If I have a glass, say a wine glass, and I put a solid in there, I'm going to see space at the bottom where the solid kind of sits on top, right? It doesn't just fill in all of the space of the glass. Wine, on the other hand, if I pour in, it'll fill everything up to a certain point. That is a liquid, okay? Now, a gas will completely expand to fill the space of the entire room that it's in, okay? So, in that sense, liquid has to kind of conform to gravity. Gravity pulls it down and it fills uh, the shape of the container, is how they use it here, that it's in. You'll see the wine glass. But a gas will fill the entire space of the room, okay? It just kind of floats around. Some other little things are the particle closeness. The way that these states kind of move and their properties have to do with how tightly packed these atoms are. Okay, so a solid is all very tight together, slammed in so tight together that they can't move. Okay, they're connected in some kind of way, and that's what holds their shape and volume together. Okay, and in a liquid, they're more pliable. Okay, they kind of wave and bend and move, and then that's what allows them to kind of flow. They move in a sense like an ebbs and flows, right? Um, they're not as tightly packed, and so that allows for that movement, right? And then gas are not packed at all. Okay, they're like individual particles that are just floating around, bouncing into each other, bouncing off the walls, coming back. They never stay connected to each other, like is the case in liquids and solids. Okay, so liquids and solids both have these attractive forces that kind of hold them together. Solids much more so than liquids, and both much more than gases. Gases don't hold together at all. Very loosely packed, particles far apart. They move fast because they have a lot of energy bouncing off all these walls and stuff all the time. And it fills the entire shape, the entire volume of the container. Okay? Okay, so here's some comparisons, and I guess this is kind of common sense, but might not be. So gases move more. We just said all this though. A solid doesn't move as much because it's tightly packed. Liquids move a little bit more. They're a little loose. They can kind of cut between each other and get around each other. But gases are just all over the place. Okay, so these are just you'll see these throughout the class. They're called trend lines, and it says that as you go from solid to gas, the temperature goes up. Okay, we'll talk about temperature here in just a second. Um, Molecular motions, which is those movements I was talking about, they go up as you go from solid to gas. And interactions, so those attractive forces or whatever, that's what they're calling the molecular interactions. There's more attractive forces on the solid end than there are on the gas end. And we've said all this. This is just an illustration of that through something called trend lines. And you'll see this on the periodic table and some other places. Okay, identify each description as that of particles of solid, liquid, gas. Has a definite volume, but takes the shape of a container. So a definite volume. Remember, a gas fills the volume of the space, so there is no definite volume. It could be infinite if it's outside. So definite volume means it has to be a solid or a liquid, but it fills the shape of the container. So that's like the wine. It goes all the way to the bottom of the wine glass. I don't see any air underneath it. That'd be a liquid. Okay, so particles are moving rapidly. Well, let me go back up to my trend line. Molecular motions go up as I go to gas. So gas is on the fastest end of molecular motions. So it moves the most rapidly. Particles fill the entire volume of a container. If you hear volume of a container, that's got to be gas, because liquid just falls to the bottom. It doesn't fill the entire volume of the wine glass. Particles have a fixed arrangement. The only one that has a fixed arrangement and cannot move is a solid. Particles are close together but does move. That has to be a liquid, right? We say they can move a little bit, get past each other, but the particles still stay connected somewhat. So that's got to be a liquid. Okay? States of matter. All right, vitamin tablets have to be a solid. They stay tablet form. I can't just drop it and it fill out the bowl. Eye drops fill the shape of their container, but not the entire volume, so it's a liquid. Vegetable oil, same thing. It fills a container, but not the volume. A candle is a wax. I melt it down, but when it's in candle form, it's solid. Air in a tire fills the entire volume of the tire. So that's a good example of how you could fill an entire volume with a gas. All right. Okay, so we're going to talk about the different properties of matter. There are two different properties. They're called the physical properties and the chemical properties. Let me go back to the text just to make sure there's nothing that I am skipping over. The slides kind of, they're the same stuff from the text, same pictures and examples for the most part, but I just want to make sure I don't miss anything. Okay. Yeah, so physical properties, and for those of you, I guess, that need to look at the text, I can kind of stop on each page a little more. But it's the same things that we've been talking about: heterogeneous, homogeneous mixtures, solid, liquid, gas, the states of matter. Now we're at physical properties and chemical properties, okay? So a physical property, when I talk about physically changing something, I'm talking about either the states of matter, so I have changed it from a liquid to a gas or from a liquid to a solid. These are different physical states of matter and a physical property, okay? So chemical changes would mean I am changing the actual chemical composition of the material, okay? So that can be a little abstract. We're just getting into all this, so let me kind of try to find some examples. Water boil. I think we got something here. Let me see. There's some in the text. Here we go. So physical changes. If you observe a physical change, a change in the state, a change in the shape, but no change in identity of composition of the substance. So water boils to form what we said, if it turns from a liquid to a gas, that's a physical change. Sugar dissolves in water to form a solution, so that's essentially a sugar going from a solid to a liquid. So that's just a physical change. Copper, you change the shape of copper into copper wires. That's a physical change. Pepper, if I cut it up into smaller pepper, it's still pepper. Those are all just physical changes. Now, if I change the chemical composition of the material, that would be a chemical change and would lead you to believe that there's been a reaction of some sort. Okay, so chemical change. An example would be rust. Okay, iron. Um, when it's first manufactured, is like a shiny metal, but as it interacts with oxygen, the oxygen combines with the iron and makes iron oxide, which we know is rust, and it starts to rust. But that rust, I can't take it back and make it the iron again. It's pretty much started to break down and wither away. It's changed its chemical state. Okay, so it is a chemical change, and it is completely different than the original iron that I had. So those are, you'll see a bunch of these on Mastering Chemistry. I think they go through some concept maps or whatever. Um, Speaking of which, if you run into problems with Mastering Chemistry, you might want to try to do a different internet browser. Some of the internet browsers have like pop-up blockers and stuff that don't allow you to submit the work. Um, I think I use Google Chrome for most all of the stuff I do, and it seems to work fine. But you just be careful about that. I think different browsers have different like pop-up blockers that keep you from doing the assignments. So just throwing that out there. Um, so physical properties and chemical properties have to do with those physical states. Okay, so like the temperature is a physical property. The color would be a physical property. Um, Let me think of some more examples. Let me see if the book does anything with that. Oh yeah, so I do have a summary of physical and chemical properties. So physical properties are color, shape, odor, luster, which I guess is how shiny it is. I don't know. The size, melting point, density. And then the chemical property is just a characteristic that indicates the ability of a substance to form another substance. So paper can burn, iron can rust, silver can tarnish. So if it can undergo a chemical reaction, whatever that property is that allows it to go, the reaction is the chemical property. So I don't know how they'll ask you that. I don't see anything about chemical properties in the examples. So yeah, I mean, you will be able to realize the chemical changes, right? So if paper burns and it becomes some kind of smoke, I can't get the paper back. That's been a chemical change. As we said with the iron rust, I can't get the iron back. Silver tarnishes, I can't get the silver back. Um, but changes in size and the state of matter, like I can turn a liquid into a solid, then turn the solid back into the liquid, so they go back and forth. That's kind of how I think about the difference in a physical and chemical change, is whether or not I can change it back. If it's a physical change, then I can. If it's a chemical change, I probably can't. Okay, so that should be fairly straightforward. Let me see what's next. I've got so many little things going on here. Some more examples you can kind of test yourself. Um, Temperature. Okay, everybody knows what temperature is, right? It's a measure of how hot or cold something is, um, measured using a thermometer, and in the SI units we use for this is Celsius or Kelvin. Okay, Fahrenheit is an English system that we don't use that much. So try to use Celsius or Kelvin. Remember, Celsius and Kelvin are directly related. It's just Celsius minus 273.15 equals Kelvin. Is that right? No, plus 273.15 equals the Kelvin temperature. So negative 273.15 is 0 degree Kelvin. All right, and that's also called absolute zero. So you will need to know how to go back and forth from Fahrenheit, Celsius, Kelvin, and there is a formula right here, okay? And my iPad ain't working, so I wanted to do some examples of that. I think I may wait. I'll talk about it. I won't do an example. I'll come back and do an example when we go over the next section, because we're going to have some more energy problems, and in a sense, temperature is an energy problem. Okay, so anyway, temperature at which water freezes. So remember, I don't know if you're paying attention in yesterday's lecture, I said that we set up the Celsius scale based on the boiling point and freezing point of water. So water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. Okay, the whole Celsius system is based on water freezing and boiling. Temperature at which water boils would be 100 degrees Celsius, so that's not right. 32 degrees Fahrenheit is freezing, so that's not right. 373 degree Kelvin. Remember, Celsius is 273 plus Celsius equals Kelvin. So if I subtract 273 from this, I get 100. That's 100 degrees Celsius. That's the right answer. All right, how many Celsius units are between the boiling and freezing points of water? We just said from 0 degrees to 100 degrees, so 100. All right. On the Fahrenheit scale, that's 1.8. Well, this is just showing you why the formula is what it is. So 0 degrees Celsius is 32 degrees Fahrenheit. So you have this little 32 on your equation. And then 1.8 is the ratio between degrees Fahrenheit to degrees Celsius. So this is how you figure it out. Like I said, I'll do some practice problems. I may post a YouTube video today is what I'll do. I'll post a YouTube video that kind of works through some of that, so you'll get to see that. Okay? And then here's the Kelvin scale. I said you just add 273 to Celsius to get Kelvin, but the units go up at the same rate. 1 degree Celsius is also 1 degree Kelvin. Okay? I mean, if you're moving, it's 273 difference, but it also moves up at 1. So what does that mean? 0 degrees Celsius is 273 degrees Kelvin. 1 degree Celsius is 274 degrees Kelvin. So if I move up 1 degree Celsius, I also move up exactly 1 degree Kelvin. They're the same, they're on the same scale. Okay, so here's some temperature checks, blah, blah. And then it moves into energy. So temperature is a form of energy, and I'll get back into that tomorrow, but I'm going to stop there. I'm not posting Master in Chemistry just yet. I will wait till I finish the lectures tomorrow and then post the whole chapter together. But those won't be due until sometime later next week. But I think that's it. I will see y'all tomorrow. Talk about energy.